remember to use the substitution principle to evaluate the following limits. So once again, the idea behind the substitution principle is thanks to all the basic limit properties and the limit laws. Unless you're trying to divide by zero, or you're sneaking up on one side of a piecewise defined function, you can get away with evaluating the limit by plugging in the limit value. So for example, on our first example here, as x is getting close to -1, x squared is going to get close to -1 squared. 2 times x squared is getting close to 2 times -1 squared. 3 times x is getting close to 3 times -1 plus 1. In the denominator, we do have a square root, but as x gets close to -1, that radicand down there, x plus 5, that's getting really close to 4, which is well away from 0. So I can just simplify this. -1 squared is 1, times 2 is 2, plus 3 is 5, plus 1 is 6. -1 plus 5 is 4, square root 4 is 2, and so my final answer is 3. Now we won't be talking about exponentials and logs until the end of the semester, but you may recall from algebra class these functions have no surprises to them, except the natural log. You have to be careful near 0. But it says use the substitution principle, so as x gets close to 0, e to the x gets close to e to the 0, e to the minus x gets close to e to the minus 0 over 2. You may recall that any non-zero number to the 0 power is 1. So 1 plus 1 over 2, 2 over 2, which is 1. Last but not least, we have the natural log. Once again, you may remember from algebra that the natural log gets funny around 0. Fortunately, we're heading into x equals 1, so we can use the substitution property. You might remember that the natural log of 1 is 0, and so we get 0 minus 1, which is -1. And I'll leave it to you to check these answers numerically and graphically if you so choose. So that'll do it for that example.